Class discussion time. We're here with Kelsey.
Hello.
And Jana.
Hi.
Braxton's here, but she's not in geometry, are you, Braxton?
No, I'm not.
Okay, good. Braxton, we'll be getting back to you pretty soon. All right, so we're going to look at the old guy talking. Here's the old guy talking to Kelsey.
Yes.
All right, so look, I could like zoom in on my nose. No, let's not do that. All right, so the old guy talking to Kelsey. Kelsey, let's say we have a theorem
All right.
in Euclidean geometry. The sum of the angles of a triangle add up to 180.
Yep.
Is that theorem true in hyperbolic geometry?
Nope.
It is not true in hyperbolic geometry. This means that that theorem relies on the parallel postulate. It depends on the parallel postulate. Now, Jana, you're up. The sum of the angles of a hyperbolic triangle add up to be less than 180 in which geometry? Hyperbolic. And that means that that theorem depends on the parallel postulate or not.
It depends on the parallel
It does
postulate.
depend. It depends on whether the parallel postulate is true or false. In this case, the parallel postulate negated forces the sum of the angles to be less than 180. So when we're saying stuff is independent of the parallel postulate, it has to be something that doesn't matter how the parallel postulate is. So let's draw one. Here's something that doesn't matter how the parallel postulate is. These two angles, I'm going to call them 1 dot and 2 dot. The 1 dot and 2 dot angles in Euclidean add up to 180.
Mm-hmm.
Doesn't matter whether we have one parallel to a given line through a point not on that line or not. In hyperbolic, the same thing. But this one's a little bit trickier. How do we know that these two angles are supplementary? Well, you can say, well, their exterior sides lie on a line. But if you really wanted to know why it was true, you'd have to say, okay, look, we'd have to do the tangents. And the tangents look just like the Euclidean case. So that's one of the things that happens. So if the angles are if adjacent angles with exterior sides on the line are supplementary, is true in both geometries, does that theorem depend on the parallel postulate? And the answer is no. It's independent of the parallel postulate. That's what it means to be independent. And usually the independent stuff is relatively simple. So like what's another one? Vertical angles. So same drawing actually. Vertical angles are the angles that are opposite each other in this letter X. Mm-hmm. These two are the same size in Euclidean vertical angles. Mm-hmm. In hyperbolic, these two with the 2 dots are the same size in hyperbolic vertical angles. So here's something that's true in both geometries. Mm-hmm. Vertical angles. So the property of vertical angles being the same size. Independent or dependent?
Independent.
She is correct. Very good. All right, let's try something else. One of the weird things that happens in hyperbolic geometry is the area of the triangle is equal to pi minus the sum of the angles. That's the area. That is hyperbolic triangle area. That's a very weird theorem. So one of the things that happens is the triply asymptotic triangle, all angles of 0, has the biggest area. Isn't that weird? So what we've drawn here is 3 triangles. Jana, you just point to them. Show me the triangle has the smallest area.
The triangle has the smallest area.
And show me the triangle has the biggest angles.
This one has the biggest
Same
angles.
one. Show me the angle with the biggest area. Triangle with the biggest area. There we go. And the smallest angles. That's how it goes. Now, that is definitely not Euclidean.
Nope.
So we're going to ask Braxton. Braxton, this theorem about the area of a hyperbolic triangle, is it dependent or independent of the parallel postulate?
It's dependent, of course.
Oh, she's a rock star. Oh my God, it makes perfect sense to her. Thank you so much. Well, I hope that discussion was enough. Was that good?
That's good.
All right, there we go. 4 minutes, guys. I'm just